Thank you very much. So I'm going to give a high-level overview of integrative analysis in network neuroscience. My talk is going to build a little bit on the presentations of Rick and Alex. And I think it's useful to start at the very beginning. Let's ask ourselves this big question, which sometimes gets lost in this whole kind of academic game. What is the aim of scientific research? Okay, the answer to this question is fairly simple. I'm going to use the OECD definition, but there are probably others that work just as well. And the answer is to increase the stock of knowledge and to devise new applications based on available knowledge. Okay, the emphasis here is to increase knowledge. Okay, so the next question is going to be, how are we going to do this? How are we going to increase our knowledge? Specifically, I'm going to talk about network neuroscience, but again, let's take back a step and look about it from a general perspective. Okay, so how do we do this in general? How does science work? Science works by building models. And models, by models I mean in kind of a very general sense. This could be like a qualitative description, or it could be a full-blown theory. But in general, we have some model of the data, and this model is based on some kind of existing knowledge. We call the model confirmed when it is relatively simple, when it has high explanatory power and high predictive power, and self-consistent, etc., etc. So now we have this confirmed model, and we want to make progress. We want to increase our stock of knowledge. How do we do this? We do this by specifying a new model, and this new model can be based on completely new knowledge. It could revolutionize the field. It could tell us that everything we knew before was wrong. We just have to do something completely different from the beginning. But more commonly, it is kind of based on new knowledge, which is built on top of knowledge that exists before. Okay, so it's a kind of an additive model, a model that becomes more complex. And both of these cases are fine. I think both of them fall well within the scientific pursuit of knowledge, but the key question comes when we want to now claim that our models are in fact should in fact replace the current gold standard. Okay, so we have to perform model confirmation, and model confirmation essentially refers to the comparison of these new models that we wish to propose with previous best available models, one model or perhaps a candidate of models. And we do this typically using objective criteria which balance between the goodness of fit, the goodness of explanation of prediction versus the complexity of the model. I can talk more about this a little bit later on. So what we don't want to do, however, what we don't want to do to confirm our models is build this straw null model. Okay? A straw null model which is constrained by some kind of partial knowledge that we picked from our existing set, and that makes it quite easy for us to confirm whatever we wish to propose. Now, if we do this, we're not adding to the stock of knowledge. Okay? We essentially just specifying something, we're telling a story, but who knows what this means, and in specific cases, when the new knowledge can be explained as a combination of existing knowledge, we're just going around in circles. Okay? We're just describing new things, using a new language, but essentially referring to exactly the same phenomena. We can describe this more quantitatively using more precise language of regression analysis. So here's a confirmed model of the data, which consists of P regressors, and now we propose a new model, which now has P+1 regressors with this XP+1 is our new putative important feature. So what we don't want to do is we don't want to test this univariable model. We don't want to use this univariable model as our null hypothesis. Okay? So how do we do this? What should we do about this? Well, there are three things. First, we should recognize and avoid just so stories. Okay? Second, we should constrain models on the full existing knowledge of evolution, development, architecture, and function. So we don't want to go back to univariable models. We want to continue with our full models. And third, we want to confirm models through systematic selection methods. Okay. So first, what are just so stories? Just so stories are
Is there a technician or a personnel here?
Oh.
Please don't let this chick.
Can you put a minute back on?
I'll go check.
Okay. So just so stories are, as you can see, the term is so offensive to this to this venue that it triggered a reaction. Okay. But they're generally suggestive and profound models of the data that are easy to devise, but fairly difficult to falsify. Okay? You build something, you use a suggestive terminology, you use maybe some kind of framework which allows you to confirm this model fairly easily, but there's actually no causal or empirically grounded evidence for this model, specifically that this model mediates adaptive function. And in some cases, you can actually explain this model using comparison, in comparison to confirmed models, which are not just so. Okay? So again, this is exactly the same thing. All I'm saying is beware of new models that appear to be profound, but that are not based on empirically grounded evidence and have not been compared to previous best case candidates. So let's talk a little bit about existing knowledge, which is the second important aspect of this framework. This is very important. We have to keep in mind what we know about brain organization and function. You know, I think that we do know quite a bit. We know that, for example, the brain is a biological system. It's embedded within the body, and it's a subject to to evolution by natural selection, selective pressures. And network neuroscientists frequently refer to this aspect, but they don't take into account the full picture again. So what tends to happen is that they describe some kind of architecture that produces some kind of utility and is then acted on by evolution through selective pressures and is gradually optimized to maximize this utility in some way, or provides an optimal trade-off between distinct objective functions. But what tends to happen, and this is part of the picture, of course, there's selective pressures, but in addition to the selective pressures, of course, the architecture is subject to phylogenetic constraints, which essentially mean that you cannot traverse a genotype space from one point to another. You get stuck in local minima, for example, and developmental constraints, which means that rules of development prevent the formation of certain phenotypes. And finally, if you like, the final common pathway of this constraints are architectural constraints, which mean that the presence of certain architectural features in your network give rise to other byproducts, as Rick and Alex have already described earlier. And you know, you have the influence of environment, which I'm not going to talk about here. So what do we know about developmental constraints? I think we know quite a bit. We know that studies over the past several decades have shown that there exists deep homologies, so homologies at the level of gene expression in vertebrate and invertebrate systems, in flies and mice, for example. And second, more recent studies, including by the neuroimaging communities, have shown that patterns of gene expressions are tightly coupled to patterns of anatomical connectivity. And together, these similar design, similar gene expression in flies and mice, as well as couplings between gene expression and anatomical connectivity, suggests that we have very similar, probably evolutionary, developmentally mediated constraints on the formation of anatomical connectons. Now, what about anatomical constraints? Rick has already shown the picture of spandrels. When we think about some architectural system, we tend to think about it in terms of its basic causes, the primary features that are relevant to its function or design, and the combination of these features. So, for example, take a triumphal arch. We have the frame, the pillar, and the arch. They interact, and they give rise to empty spaces, which are known as spandrels. Now, a person who does not know sufficient, does not have sufficient information about formation of arches may look at a richly decorated spandrel on the right and think that spandrel was in fact the cause of this formation. But in fact, the spandrel here is a byproduct. And I'm glad that this issue was appreciated by the OHBM community because they essentially placed spandrels on the front of the program. So as I previously described a couple of years ago now, if you take modules and hubs as the basic framework of brain networks, then you get cores and clubs, if you like, one of the most important discoveries in network neuroscience, for free. You get them as byproducts. And so, again, coming back to our first question, this does not actually increase our knowledge. We're not actually doing
science here, all we're doing is we're kind of going around in circles. So this is very important to emphasize. It is a very important point that we need to think about collectively as a field in order for us to make grounded progress. Okay? So how do we do that in practice? Okay, so say we think about constraints and we specify these constraints. How do we actually compare models in real life? We do this through systematic model selection, and in practice, you can think, again, going back to regression, you can think about regression analysis as a useful analogy. So in regression models, you have some data set, and then you fit a model to it, and then you describe this fit in some kind of biological context, and then you use this fit to generate new realizations of the data, and then you use these new realizations to test for new hypotheses, for example, or to predict new instances of the data. So exactly the same thing can be done in network neuroscience. You can start with a connectivity matrix. You can fit some model to it, for example, a community structure or hubs or something else, something that's important. It doesn't have to be a structural model, could be a dynamical model. And then you sample networks with these constraints and see whether this sampling allows you to predict other emergent phenomena. So at the top here are the original networks, and at the bottom here are the ensemble realizations, averaged over ensemble realizations. This is a connectivity matrix, of course. And in practice, the key to this process is unbiased sampling of networks with constraints. So what you do essentially is you specify certain constraints, which are your basic hallmarks, the foundational features of the system, and then you seek to sample uniformly or unbiasedly networks from the space that is from the space of these constraints. Okay? And you can do this in two ways. The first way is based on simulated annealing or similar Markov chain Monte Carlo algorithms. The idea is that you start with some kind of random configuration, and then you gradually rewire it towards a state in which it satisfies the constraints you imposed. This is in principle a very general and very powerful framework, but it's computationally slow. It does not scale well to large data sets. An alternative is where you start with some kind of configuration which is you start with a different configuration based on sampling of networks directly from the probability distribution which satisfies these constraints. In principle, you can do this using a you can think of it as a kind of a mean field formulation where you satisfy the constraint on average in the full ensemble, but you don't satisfy the constraints in every individual network. So this is like sampling with soft constraints. This is fairly fast. It scales well, but one of the problems is that it makes independent assumptions between for edge formations, which are often unrealistic. So I'm going to release a toolbox later this year that is going to include these methods, and I hope that this will spur investigators on to trying to test these hypotheses in a more principled way. And again, going back to the first question I posed, this is the idea here is that if we test this hypothesis in a principled way, we can then build on existing knowledge and we can advance knowledge forward. Okay. I'm going to quickly illustrate an example that is actually I performed with my collaborators at Janelia, Howard Hughes Medical Institute, where we studied zebrafish. And I'm just going to describe what we did. So we looked for specific adaptive behaviors, and then we found correlation, but also loss and gain of function evidence for this behavior. And finally, we performed model confirmation. We used the larval zebrafish as a model, and we looked at this behavior associated with so-called giving up when the fish stops swimming. And what we found is that a group of regions in the hindbrain lit up when the fish stopped swimming, and we performed causal manipulation to show that, in fact, there was some kind of causal relationship between this behavior and the swimming of the fish. And what we found essentially in the end is we reconstructed a circuit associated with mismatch detection which led to noradrenergic granules in the medulla, hindbrain astroglia, which then in the end shut down this behavior. And you can think of it as a kind of module, and more generally, you can find many of these modules in the data. And if you constrain your models on these modules, you can reproduce the data fairly to a fairly high degree of precision and accuracy. So in conclusion, the take-home message again is focus on specific utility, avoid just those stories, specify fully constrained models, and systematically select models through unbiased network sampling. So, and I think this is a very good quote that captures the philosophy of this endeavor. It is the task of science to reduce deep truths to trivialities. Thank you very much.